I'm so excited to talk to everybody. I don't seem to have my mouse in order to move the Zoom stuff over. So let me see if I can move maybe I need to minimize this first.
You know
It's
what
not
I do,
blocking
Beth?
my screen.
I escape from the full screen and then you'll get your tools back, I think.
Right, yeah. So, so welcome everybody. And I know it's the end of a long day full of activities. So I hope that, we'll just go through some fun science, and I'm excited to, take your questions and clarify anything that doesn't make sense. And I hope that this follows from the conversation you had with Eric earlier today and your activity playing with water, because that ties into thinking about abrupt climate change. So a little bit about me. I'm a professor at Colby College in Maine. It's a small school in central Maine, and I teach in the geology department. And I did my undergraduate work at Carleton College in Minnesota, and then my PhD at University of Maine in Earth and Climate Sciences. And then I did 2 postdoc positions, one at Lamont Doherty Earth Observatory in New York at Columbia, and the other at Dartmouth with Eric Osterberg. So I was fortunate to spend a couple years there, and got actually involved in a project in Alaska where you see this photo here. This is at the Denali Base Camp, where I got to go for 2 different summers to do research as part of Eric's group. So that's been really a great opportunity. And mostly I work in Antarctica, and I've also been doing research in New Zealand, Alaska, and some other parts of the world. So I want to start with kind of a broad question. I don't know why the Zoom menu just popped up covering my slide. There it goes. And the broad question is, what drives global temperature patterns? So we need to think a little bit about global climate and mechanisms kind of driving global climate patterns as we kind of get into this narrow topic of abrupt climate change. And so if we were in a classroom, we would, break into small groups and think about this pattern of temperatures that you see here. But since it's more of a presentation, I'll just plow along here. So hopefully when you're thinking about the shape of the world and the fact that it's a globe and not a big rectangular map like this, you're realizing and thinking about how the sun's radiation interacts with the surface of the earth, right? And so most of that heat energy is absorbed in the tropics and very little in the polar regions. And so we end up with this pattern of much colder climates, of course, in the north and south poles, and really warm climates in the low latitudes with these gradients from the tropics to the poles. And so when we think about what Earth's climate system is, looking at this blue marble photo from space, where we can see the ocean and the clouds, so representing the atmosphere, we can think about Earth's climate as this big mechanism that's trying to move that excess heat from the low latitudes up to the polar regions that are much colder. And so what we're actually seeing here is the effects of convection in the ocean and atmosphere moving that heat around, okay? So this is kind of my, in a nutshell, overview of what Earth's climate system is that I teach my students in my climate class. It's a big mechanism that is trying to redistribute heat around the planet, okay? So I hope you can see this. This is an animation from NASA that shows different types of particles in the atmosphere blowing around in the winds. And I like to show this for a variety of reasons. But for us today, what's relevant about this animation is that we can actually see the global wind belts. You can see that in the tropical regions, you have the trade winds that are generally moving from east to west. So you can look at the dust from the Sahara and how that is generally moving across the Atlantic Ocean as it's doing right now. Maybe some of you are underneath that Saharan dust cloud in the southeastern US. And then in the higher latitudes up in Maine, where I am, we have the westerly winds, right? And so you can see those big wavy blue bands of storms moving from west to east in both hemispheres, okay? And so the atmosphere is composed of different cells that are moving heat through convection. And you just spent some time looking at ocean temperature, thinking about ocean temperature and thermohaline circulation. And so we basically have these two mechanisms, the ocean and the atmosphere. And as both of those circulate around the world, they're able to carry heat with them. Okay, so this is the foundation of Earth's climate system. All right, and so we can actually graph that heat transport that's done by both the atmosphere and the ocean. So this is a graph showing heat transport in petawatts, which is just a lot of watts. I think it's 10 to the 15th watts, as a function of latitude, okay? And so let's just focus on the northern hemisphere. So from the equator to the right, looking at the northern hemisphere, and we can see that the total heat transport in blue peaks in the mid-latitudes, around 40 degrees north. And if we look at the two curves underneath the blue curve, so the dashed green and red lines, those are showing different models of atmospheric heat transport, right? So we said that the ocean and the atmosphere are the two mechanisms moving that heat from the really warm tropical latitudes to the cold high latitudes. And if we look at this, we can say that the difference between the total heat transport in blue and the atmospheric curves in red and green is what would be the ocean, right? And so you can see that actually the ocean plays a really big role between the equator and the mid-latitudes, and then the atmosphere is actually really important from the mid-latitudes to the high latitudes, okay? So I hope that that makes sense. All right, so how exactly is heat transported by these ocean currents, right? You have your warm, less dense water, your red water, and your cold blue water. And of course, we're using the same color scheme here, so that makes it easy. But basically, we have these warm currents that carry water that's heated up in the low latitudes near the equator, and those are called western boundary currents. And the Gulf Stream in the Atlantic is our local example. So you can see that extending from Florida up past Newfoundland and up into the North Atlantic, right? Every ocean basin, North Atlantic, South Atlantic, Indian Ocean, and the North and South Pacific, they all have these warm western boundary currents. And those are in the boxes on this map, okay? So some are warmer than others. But you can see that there's a lot of heat being transported by those currents from the low latitudes to the high latitudes. And conversely, cold water from the cold polar regions is also flowing back toward the equator, yeah, as eastern boundary currents, which are cold, okay? So you can see those blue currents, which are maybe a little bit less obvious. They tend to be kind of wider and they don't flow quite as fast as the western boundary currents. But this is just showing us sort of what happens at the surface. And the surface is only part of ocean thermohaline circulation. It's really just the easy stuff to see. But what's actually happening is that water, of course, is sinking where it gets really cold and salty. And it actually goes around the whole world before it makes a circulation sort of back to where it came from. And this was the original graph or drawing of this idea by Wally Broecker, who was a scientist at Lamont Doherty Earth Observatory at Columbia for over 50 years. And he just passed away 2 years ago. But he was really the grandfather of paleoclimatology. And he came up with some really important ideas. And we're going to talk about two of those ideas today. So one of those is the idea of the ocean conveyor belt. So it's the idea that this hot, warm, salty water, which you see as the Gulf Stream. So if you look at the North Atlantic and you look at that red arrow moving north, of course, it's drawn on the wrong side of the ocean basin. So imagine that's actually over by North America, which is where it should be. But then you can see those red arrows kind of releasing the heat into the North Atlantic and up into Europe. So that's what the Gulf Stream does. It releases a lot of heat, and then it's already salty, and it's now cold. So if it's cold and salty, that makes it more dense, and so it sinks. So that cold North Atlantic water sinks down and travels all the way around the ocean basins. And that's shown by this dark blue or purple arrow that kind of goes into the Indian Ocean and the Pacific Ocean, and eventually kind of comes back up to the surface. So this is a very simple, even simplistic version of what is happening with ocean circulation. But the idea is that there are places where ocean water sinks because it becomes more dense, because it gets saltier or it gets colder or both. And in those places, it then sinks down to the bottom of the ocean and slowly flows around the whole world, okay? So of course, it's more complicated than Wally's conveyor belt model. Here's a more up-to-date version, just focused on the Atlantic, showing where the currents are. You can see the surface currents in red and the deeper currents in blue. So there are these different regions where the warm water gets cold by releasing its heat and where it sinks. And you can see those places between Iceland and Norway, where you have the red arrow converting to blue, and also near Greenland, so red converting to blue. So that's indicating sinking of that water, all right? So you see that there are lots of different smaller scale circulations happening as this water flows around. So it's not just a perfect conveyor belt, but the idea is pretty clear from Wally's initial conception that the water moves around the world, and it takes about 1,000 to 2,000 years for it to get back to where it started from, okay? So again, it's driven by differences in density that are caused by changes in ocean temperature and ocean salinity. And so you could think about, how does ocean water get saltier? There are two major mechanisms. One is that you take the water with the salt in it and you lose some of the water, but you keep the salt, right? So that's what happens during evaporation. Water gets saltier. As water evaporates, the salt gets left behind. So that is how warm water in subtropical latitudes gets really salty. So that's happening in our Gulf Stream. The other mechanism is, as sea ice forms from that ocean water, sea ice doesn't like to have salt in it. The ice structure actually kind of kicks the salt out, and that puts more salt into the water. And that process is called brine exclusion. So that happens anywhere that sea ice forms. So that's near Antarctica and up near the Arctic Ocean. Okay, so that's kind of how water gets denser. And as it gets denser, it can then flow around the world. All right, so here's a picture of the Gulf Stream, which you've seen before, carrying that warm, salty water up to the North Atlantic. So the goal of our talk today is to look at how changes in ocean and atmospheric circulation play a key role in driving abrupt climate changes. These are changes that happen on timescales of tens of years. So things that happen really fast in the climate system. So what I hope you get out of this presentation today is to identify the structure of ice age cycles from ice and marine core data. You've started to do that already, so we'll just cover that fairly briefly. And then we'll look at Greenland and Antarctic ice core records to see how they're similar, but also how they're different. And then we'll evaluate the timing and phasing of abrupt climate changes during the last glacial period using ice core data. So we'll look at when they occur and how they occur between the hemispheres. And then that will in turn allow us to assess the mechanisms that are driving these past changes. And that will bring us back to thinking about ocean and atmospheric circulation. All right, so as I think you've already seen, maybe some ice core data looking at ice age cycles. Here is a graph from Antarctica showing the last 130,000 years, where we're looking at the present on the far right and the full last glacial cycle from the last interglacial period, when this black curve was at its maximum peak with a value of about negative 365 or so. This is an isotope ratio that is used to reconstruct temperature. So we can just think of this as a proxy for temperature, something that tells us about temperature. And so when we go in the downward direction, we're looking at colder temperatures, and in the upward direction, warmer temperatures, right? So we can see that most of the time during an ice age cycle, the Earth is actually in a cold phase, right? It's colder more of the time than it is warm. And we can also see that there's this really asymmetric pattern. So the Earth cools really for a long time. Most of the cycle is cooling down into the maximum cold period, which we call the last glacial maximum. So the last peak ice age conditions around 20,000 years ago. And then a really rapid warming up into the modern warm period, or called the Holocene. Okay. So this asymmetrical pattern, as you've already seen, is repeated in Earth's ice age cycles. If we look at all of the ice age cycles that we can see from ice cores from Antarctica, so 800,000 years, and we look not just at temperature, which is now shown in black, but also at CO2 in red, and also the global sea level curve in blue at the bottom, we can see that those three things track each other really, really well. So when CO2 is high, global temperature is high. When CO2 is low, temperature is low. And we see that global sea level, which is driven by changes in the volume of ice that's stored on land, so the ice sheets, that is also tracking temperature and CO2, okay? So the whole world's climate is really going in sync, sort of inhaling and exhaling on the same time period with the same cyclicity. Now it gets more complicated, okay? So you've already seen those ice age cycles, and now we're gonna look at the differences between Greenland and Antarctica. It's also more tricky because this plot has the x-axis going the other way. So just a heads up, and I've tried to label the slides where it changes direction. So now the present day is on the left, and 140,000 years ago is on the right, okay? So we've been looking at records from Antarctica, and maybe Eric talked about why those records are longer than the records from Greenland, but they're longer because the ice is older. We can't get ice that old from Greenland because it's in a warmer location and the ice sheet is not as thick and it melts and flows out to the ocean. So in Antarctica, we can go back over a much longer time period. And as we'll talk about tomorrow, there might actually be ice that's as old as 1 or 2 million years in Antarctica that we can actually measure and learn about even farther in the past climate. All right, so let's look now at the details. So overall, Antarctica, shown in the upper panel from 2 different ice cores, and Greenland, showing 2 cores from Greenland in the lower panel, they follow the same general patterns. So around 130,000 years ago, both hemispheres were pretty warm. That was our last interglacial period, so time in between the ice ages. And then both hemispheres show this cooling down into the maximum ice age around 20,000 years ago, followed by a rapid warming called the deglaciation, and up into the Holocene, which is a sort of relatively flat warm climate period that we've been in for the last 11,700 years. But after that, the patterns are totally different, right? So if you look at Greenland, you see these really abrupt changes in this proxy. So this is delta 18O on the bottom plot, and we're looking at delta 2H, which is delta deuterium. So they're both isotopic measurements of the water composition, and in both cases used to infer temperature. So basically we can say that temperature in Greenland is fluctuating back and forth, back and forth, back and forth really rapidly during the ice age period, or the glacial period. Whereas in Antarctica, we see that there are these little wiggles, but they're more gradual. The timing might be similar, but the pattern itself is really different, okay? So that's what we're going to dig into when we think about abrupt climate change. We're looking at these events in Greenland and their relationship to what's happening in Antarctica. So we're going to focus in on the next slide on this period from about 30,000 years ago to 50,000 years ago. Okay, and just looking at Greenland ice core data. So again, this is delta 18O. This is our isotopic proxy for temperature. Time is still going to the present on the left, so that's consistent with the previous slide. But now we're just looking at those abrupt climate periods. These are called Dansgaard-Oeschger cycles, named after the two scientists who discovered them. And what we see is that there's semi-cyclic intervals of rapid climate change. Specifically, we see warming, so that going from low to high on this graph represents rapid warming. And that's about 5 degrees Celsius in about 30 years. That's the kind of scale of abrupt climate change that we're talking about. So there's that rapid warming, and then you kind of hit a peak in temperature, and then a gradual cooling followed by a couple hundred, plus whatever years, up to a couple thousand years of cold temperatures before the next event. But you see that this pattern is repeated over and over again over this 20,000 year period, okay? We don't see that same thing in Antarctica. So now let's look at what we see between the two hemispheres. All right, so now we're gonna throw more records at you and flip the direction because every publication is different. So now the present day is to the right and our time period is slightly greater. So we're looking at about 70,000 years ago until about 20,000 years ago. So here we're looking at Greenland in blue. And if we go back one, so you see GRIP and NGRIP. Those stand for the Greenland Ice Coring Project and the North Greenland Ice Coring Project, I think, if I got my acronyms correct. You see that those two cores are really similar. So it doesn't really matter which one we look at because this pattern is replicated between those two ice core sites. So this plot in blue is showing the North GRIP oxygen isotope record. So that's the top record, Greenland, record A. And then the next one down is showing, and all three of the lower records are showing data from Antarctica. The green record is methane concentration, all right, from an ice core that I worked on during my PhD, the Waste Divide ice core. The orange record below that is the Delta 18O, or temperature proxy record from the same ice core. And then in purple, the bottom record is showing this Antarctic temperature stack. So it's basically an average of different ice core data showing regional temperature patterns in Antarctica. So let's just make some basic observations about the orange and purple, so the bottom two records, okay? So we have one ice core, the orange one, Waste Divide, and the purple one, which is kind of an average of multiple ice cores. And they look really similar, don't they? So when one goes up, the other is going up. When one goes down, the other goes down, which makes sense. So you have one example of a temperature record that matches up with kind of average temperature in the region. Then if you look at methane in green, the methane record, gosh, it looks a lot like the Greenland temperature record. It doesn't look at all like the Antarctic record. So when you see those peaks in the Greenland temperature record, you see peaks in the methane record. One for one, as you go across and look at those where those lines have been drawn in to line up the events, the methane is really closely tracking the temperature in the northern hemisphere, even though we're measuring it in Antarctica, right? So this gas, methane, is actually telling us something about what's happening with climate in the northern hemisphere, but it's getting mixed throughout the atmosphere so quickly that it's measured in Antarctica in the ice core, and we see no time lag. What we see is matched up with time in Greenland, okay? And that's because changes in temperature in the northern hemisphere are affecting the wetlands in the tropical regions that are producing the methane. So methane in general is produced in the tropics, but there's more land in the northern hemisphere than there is in the southern hemisphere. And so that's really why we see a northern hemisphere temperature signal in that methane record. Okay, so we'll move on to a more detailed view where we're gonna look at these events, the warming side of the Dansgaard-Oeschger events and the cooling side. So just to go back, we're basically taking these events highlighted by the yellow lines and mushing them together into these plots. So The blue is the Greenland temperature, which is consistent with the previous slide. The green is the methane record measured in Antarctica. And the orange is the waist divide ice core temperature from Antarctica. And so what we're doing now is saying that time 0 is the time when we see the greatest change in Greenland temperature, right? So we're zooming in on these abrupt climate changes. And we see that when Greenland temperature goes up, so we're looking at panel B here on the left, Greenland goes up, it's followed just by a little lag by methane going up, then they stay high for a while. It takes Antarctic temperature some amount of time after that to increase, kind of hit its peak, and then it starts to decrease. So Greenland warms up and stays warm. Antarctica warms up a little later and then it starts to cool. And if we look at these abrupt events on the cooling limb side of the Danskard-Eschger events, so again, 0 is the middle of the Greenland change. So negative time is years before that, positive time is years after that. Greenland, it starts out being warm, it drops off abruptly, it's followed by methane with a short lag until they both kind of level out again at colder temperatures and lower methane concentrations. We see that then Antarctica is cooling across that period, but about 200 years after Greenland cools, Antarctica actually starts to warm. Okay, so the overall pattern is that there's a bit of a lag, but we see that Antarctica is doing the opposite thing from Greenland. So Greenland warms up, Antarctica waits a little while, and it cools down. Greenland cools down abruptly. We're talking a couple decades here. Antarctica waits a couple hundred years or so, and then it warms up. So something here is changing between the hemispheres and the way that heat is shifting around the planet. That's what we're really finding with this mechanism driving abrupt climate change. And in thinking about why this happens, we actually come back to Wally Broecker. So he, in 1998, wrote this paper, Paleocean Circulation During the Last Deglaciation, a Bipolar Seesaw. And the idea is that this out-of-phase nature of abrupt climate change events during the last glacial period, including the deglaciation, can actually tell us something about their causes. And the fact that there's this lag between temperature in the north and temperature in the south tells us that there's this sort of seesaw mechanism working between the two hemispheres. All right, so we're going to look at these cartoons that kind of describe two different mechanisms. One is an oceanic mechanism, and the other is an atmospheric mechanism. And it turns out, spoiler alert, it turns out that that 200-year lag that we just saw is consistent with an oceanic mechanism. So it takes about 200 years for heat that was in the north to actually sort of shift to the south and then cause warming around Antarctica. So let's take a look at this mechanism. So we're gonna have to introduce another term. We've seen the last glacial maximum. Then there's this other term called stadial, which just means really cold conditions during the ice age. So if there's, so we start out on the left in the last glacial maximum. So you see that there are these black arrows, and we have some sort of ocean circulation happening in the Atlantic, and then there's this continent in the middle, which we can think of as like the Americas all together as a big lump, right? And we've got the south, which is Antarctica, and the north, which is Greenland. So in this scenario, there's heat moving. You see that blue arrow turning red. This is sort of heat kind of shifting into the northern hemisphere. There's maybe some extra heat loss, these red radiative arrows going out to space. And then we go into really cold conditions, the stadial and of extra cold condition. And the idea is that maybe extra ice gets released out into the ocean and melts, which puts a lot of fresh water out into the ocean, right? Fresh water doesn't sink, it's not dense, because we need extra salt and colder temperatures to make that water sink. So suddenly there's a stopper on thermohaline circulation with this fresh water in the North Atlantic. So what does that do? It drives the circulation to sort of back up, kind of plugs up the plumbing. And you see that that arrow that was sort of blue in the southern hemisphere and red in the northern hemisphere, now the red is shifting more into the southern hemisphere, and there's more heat being transported to the southern hemisphere. So this is an oceanic mechanism that transmits heat from the north to the south. And by doing so, it can melt the sea ice around Antarctica, which warms up Antarctica. And as these changes happen, there can be the release of CO2. And so we haven't really talked about what CO2 does during these events, but basically CO2 is playing a role in warming the climate, right? We know that. So this is the oceanic mechanism of the bipolar seesaw. So release of fresh water in the north slows down or stops thermohaline circulation, heat gets shifted to the southern hemisphere and drives Antarctic temperatures up, which we saw in our last slide. And then there's a second mechanism. So scenario B is showing us what would happen in the atmosphere. And inherent in this is the idea that the atmosphere can respond more quickly than the ocean. So here, the same time periods. So what we see is that during the last glacial maximum, there's a big ice sheet in Greenland. There's a lot of sea ice around Antarctica. And the westerly winds, which we saw early on, those wind belts are shifted a little bit toward the equator. All right, so that's what that means, equatorward westerlies. So the wind belts are shifted a little bit to the north in the southern hemisphere. Then we get into those really cold conditions in the right-hand lower right panel. Really cold in the northern hemisphere, excess ice builds up, causes melting and fresh water in the northern hemisphere. That leads to a buildup of sea ice because you have this cold, fresh water. Cold, fresh water is going to freeze. And that affects the atmospheric circulation and pushes all of Earth's circulation cells to the south. So we see a southward ITCZ that stands for the Intertropical Convergence Zone. So that is where, right now, in general, that is where air masses come together and you get a lot of rainfall along the equator. That shifts to the south and the westerlies shift toward the south. So we see poleward westerlies, and that change in the atmospheric circulation affects the ocean because those surface currents are driven by the wind. So as the westerlies shift south, they actually speed up the ocean circulation in the southern hemisphere, and that releases CO2 that was trapped in the ocean during the ice age. So you see this release of CO2. All right, so we've talked about the evidence for the ocean mechanism, but there's actually also evidence for this mechanism, this atmospheric seesaw. So here's just one paper that gives us, this is one of the earlier papers, it's from 2009. This is all fairly recent research, but it shows us some evidence for this atmospheric seesaw mechanism. So it's called wind-driven upwelling in the Southern Ocean and the deglacial rise in atmospheric CO2 by Bob Anderson, also a Lamont scientist. So he and his team looked at these cores that you can see around Antarctica, and they measured a variety of sedimentary proxies in these marine cores. And I probably don't need to go through all of these. You know, there's always lots of lines on these graphs. But let's just take a look at what kind of our graph is showing, okay? So again, our x-axis has changed direction. The present is toward the left, and we're looking at the time period from the last glacial maximum or so, 25,000 years ago, up to the present. So again, we're looking for evidence of an atmospheric mechanism. So a rapid change in the winds that could speed up the rate of ocean circulation in the south and release CO2 to the atmosphere. And that would drive warming of the climate. So this upper graph, an ACR, the blue bar in the middle stands for the Antarctic cold reversal. So it's just a 1,000 years or so when Antarctica started to warm and then sort of plateaued or got a little colder, and then it warmed again. All right. And overall, the period that's in pink, kind of pinkish highlighting, that's the deglacial period that they're studying. Okay, so this top graph is showing atmospheric delta C14. That's a mouthful. This is the amount of radioactive carbon measured in this core. Or it's changes in the atmospheric radiocarbon, so carbon 14. And the important thing to know is that radiocarbon is produced in the atmosphere by bombardment of nitrogen atoms by radiation, okay? So it's produced in the atmosphere. So any carbon, any CO2 coming from the deep ocean has been isolated from the atmosphere. And so if it gets released into the atmosphere, it will change the amount of that radioactive carbon in the atmosphere. So in other words, it will dilute it. There will be less of it, right? And that's what we see. So we see that that value is going down across this period. And the right-hand axis is saying dilution with old carbon. So carbon that does not have any of this atmospheric radiocarbon in it. The next curve is showing CO2 concentrations from an ice core in Antarctica, which we've seen before. This is the Dome Sea ice core. And you see that CO2 is going up across this period. And we know that we can measure CO2 in air bubbles in ice cores as a direct measurement of the past atmosphere. So CO2 is going up. It's diluting the radioactive carbon, the radiocarbon in the atmosphere. And at the same time, there are indicators in the next two lines of increased ocean upwelling. So increased ocean circulation in the Southern Ocean, showing that nutrients are coming up to the surface and fueling phytoplankton growth. So the base of the food web is more active because of this. This is all happening so fast, it does not allow for that 200-year lag that we see with the ocean mechanism. So here, we're seeing evidence of a wind-driven mechanism that rapidly releases this old carbon into the ocean and into the atmosphere, into the surface ocean and into the atmosphere, okay? All right, so this is my last slide. It's a lot of stuff to think about, but I hope some of the basics are sort of sticking and making sense of what you've already learned. So coming back to the idea of Earth's ice age cycles, I think Eric might have talked about Milankovitch and the idea of changes in Earth's orbit driving kind of the timing of ice ages. And what we see and understand now is that these changes in Earth's orbit are the pacemakers of the ice ages. They dictate the timing, but they're not the whole story. And Meredith Kelly's work actually also, really digs into this problem, is that Earth's climate is a complex system, and we can't explain all of what happens with ice age cycles just by changes in insolation or incoming radiation. Okay, but there's actually a lot going on with these internal feedbacks, changes in circulation, and also just noise that affect Earth's climate system. And so overall, we do see that CO2 in the atmosphere is kind of the great leveler of climate. It helps translate signals from one hemisphere into the other. And we saw that both of those bipolar seesaw mechanisms, the oceanic and the atmospheric mechanism, both release CO2 into the atmosphere because of how they affect the Southern Ocean. So I'll leave you there. This is an area of ongoing research. And this is a photo of my friend Aaron Putnam, who's a professor at UMaine, and he's actively working to help figure out some of these riddles about Earth's ice ages as well. So I will escape, and I'm very happy to take questions and hear what you all think.
So usually we have lots and lots of questions, so don't forget to unmute yourself.
Well, my question is that it was actually the question I asked Eric. So indeed, there are differences in the way that climate is changing and affecting between Arctic and Antarctica based on your presentation. And so if I understood correct, there are abrupt changes happening a lot faster in Greenland because of the, I would say, the formation or the lifespan of the ice is a lot shorter, or if I understood correct. And also, there are more lands on the northern hemisphere that you mentioned, that these are also factoring in those abrupt changes and what is happening. can you confirm on this? I just wanted to make sure that I got the good summary on what you're presenting.
Yeah, great questions. Thank you. So I guess one thing we should clarify is the difference between the changes that happened during the last glacial period versus what's happening today. Were you asking more about today or more about 20 or 30,000 years ago?
I would say that most recent, it will be like, you know, the changes that are like, especially the human history part. Yeah.
Yeah, absolutely. So you're right. Greenland is changing faster today than Antarctica. And that's mainly because it's at a lower latitude than Antarctica is. So Antarctica is centered on the South Pole and it's surrounded by the ocean. So it is a little bit more isolated. There are parts of Antarctica that are warming rapidly and places where we're concerned that there are changes that might affect people, in the next, hundreds of years or so. But because Greenland is actually not at the North Pole, it's actually, much farther south, it's experiencing more warming right now than Antarctica is. And so it's melting. That's a big problem. It's losing ice. And as it changes, it's affecting the ocean circulation as well.
Is it going to happen? Did you watch the movie called Tomorrow? What was the call?
After Tomorrow.
Yeah. Did you guys watch that? Would this happen?
No, there's a lot of inaccuracy in that movie. But now, armed with what you know, you can watch it again and ask some critical questions about that movie.
All right.
So, hey, Beth, could you comment on tie together? Do you see any correlation between rapid climate change and the thermal haline circulation current? I thought there's some evidence that current is slowing down, that they've measured that, and does that drive any of this rapid climate, or is that a different situation?
Yeah, so the mechanism that we talked about in regard to abrupt climate change during the last glacial period is, it's a mechanism that should in principle be working today. So what we are seeing is a slowdown of the Gulf Stream. It's the slowest it's been in at least 1,600 years, largely because of Greenland melting and putting fresh water into the North Atlantic. So it's slowing the thermohaline circulation. And that will and is causing impacts in Europe, changes in temperature patterns and precipitation. And over a long period of time, we might see a shift in ocean heat transport to shift some of that heat to the southern hemisphere, which would actually speed up Antarctica's melting. So certainly the whole system is connected and it remains connected, but some of those mechanisms don't happen quickly enough for us to see them with our own eyes sometimes.
How much has the Gulf Stream slowed?
As far as an amount, I don't remember off the top of my head.
And do you happen to know what percent the thermal haline circulation current has slowed?
Not off the top of my head.
I have a question. Actually, it's two questions. I understand as the permafrost melts in polar regions, it releases more methane. And then I was also reading about how countries like in England, they're trying to reestablish estuary areas to absorb more carbon dioxide. And what effect could that actually have on the global warming effect that we're experiencing?
Okay, so with permafrost thawing, there's definitely a concern about release of methane and CO2. And the other place where there's methane stored is in continental slopes. So down in the mud below the ocean, but on the edges of continents in the Arctic. So that's another reservoir of methane that makes some people concerned, although evidence suggests that it's fairly stable. As far as carbon storage in estuaries, I don't know much about that. So I can't really speak to that one.
I got a question referring back to what Bill was asking. The statement that global warming may cause global cooling. So does that hold water with what you're talking?
It's more that, global warming is still overall warming, but it's patchy. So there are places that might cool more in certain seasons and might warm more in other seasons. So we might see more extremes, and that is what we're seeing with, say, Siberia today being so hot. So there are places that cool, and right now the main place that's cooling is the middle of the North Atlantic Ocean, right up by Greenland, and that's because of all this cold water melting and going into the ocean. But if you look at, you know, large term or sort of large scale maps of global temperature patterns and temperature anomaly maps, you see that overall the world is warming. And then the impacts are a little bit different in different places. So the high Arctic latitudes are warming the fastest through a process called polar temperature amplification. So as sea ice is melting really rapidly, you have a shift from a very reflective surface to a very heat absorbing surface. So that just spirals up the temperature and causes more impacts in the Arctic right now than what we're seeing in the Antarctic.
So we talk about climate change, and then we know that overall, you know, globally we are warming. Are there any places cooling? Like, I can't remember off my head. I keep telling my students we are warming, but is there any place we actually notice it's cooling?
Yeah, I mean, the place that comes to mind is that blob of cold water just south of Greenland that you can see. But there's a great website called CCI Reanalyzer that's a way to look at a lot of climate data. And you can look at temperature patterns and differences in temperature between the modern day and, say, 40 years ago. So it's something that would be fun to explore with students if you wanted to look at that website. I can send the link.
What's the name of the website again? Can you send it? Yes, thank you.
Yeah, I'll send it afterward. It's a climate reanalyzer.
That will be great, thanks.
I
So
haven't
I
looked
have
at
a question, sort of, sorry.
Oh, go ahead.
No, I had a question sort of related to the methane question. And wouldn't the C14 also be affected by permafrost melt the same way that upwell? So I'm just wondering if how they tell the difference of the source of, if you have a dilution in the C14, if it's because of carbon that's been stored in the ocean versus carbon that's been stored in permafrost.
Yeah. So in principle, if all you were measuring was carbon 14, you wouldn't necessarily be able to just know the difference. You'd have to look at other things, like you look at the methane concentration. So if methane concentration doesn't go up, but CO2 concentration does go up, and you see a change in radiocarbon, you could probably rule out a permafrost methane source because you would also expect to see methane go up, right? And in fact, the same basic thing is happening today with fossil fuel burning, that of course, fossil fuels were created 300 million years ago during the Carboniferous. And so there's no radiocarbon in that fossil fuel. So we're burning gasoline and coal and whatever from that time period and actually changing the radiocarbon in the atmosphere as a result. So that's been something that's been measured for the last couple hundred years.
Was that what you were referring to as dead carbon dioxide? It's gone through radioactive decay and the half-life there's no more. It's just so. So the carbon dioxide from fossil fuel burning has no carbon 14 in it, or very little.
Has 0. Yeah.
Now I get it. The light bulb's on.
Awesome. Yeah. So the half-life is 5,720 years. And so anything over 50,000 that's been isolated from the atmosphere for at least 50,000 or 60,000 years won't have any radiocarbon in it.
Yeah, Dr. Bess, can you hear me? It's very interesting about the Gulf Stream. It is, you said just now, it is a huge stream and warming of European countries, but it has any effects on east coast of the US climate?
Definitely, yeah. So as the Gulf Stream slows down, it's a big mass of water. And it's actually, because less water is moving, it's sort of like it's sloshing up in a bathtub, and it's contributing to coastal flooding. And when we get hurricanes along the East Coast, because it does drive sea level up in general. It helps make those storm surges worse. So certainly coastal flooding is an impact that we're seeing. And the other big impact is that a lot of that warm water is now kind of pooling up along the East Coast. And so here in Maine, the Gulf of Maine, so that body of water contained between Cape Cod and Nova Scotia, is the warming faster than 99% of the world's oceans, because you have this really warm water from the Gulf Stream that's just like coming in. So yeah, we're seeing huge impacts with, you know, biology, and, you know, lobsters are migrating and whales are migrating. It's like, it's really hot. And of course that affects the climate here locally as well, having all that warm water here.
Oh, thanks.
Yeah, great questions.
Oh, Bess, we really appreciate you coming today. And I know you'll get a little more time with Bess tomorrow. She's going to be talking about the future of ice core science tomorrow. So if you'd unmute yourself, let's give her a round of applause.